Okay, folks, today we're going to look at planar graphs and what a planar graph is and rules that apply to planar graphs, etc. So let's see. We're not going to do the investigation. He says when a connected graph can be drawn without any edges crossing, then the graph is planar. Okay, so the graph has to be connected, and which means every edge has, or every vertex has an edge going to and from that vertex. Okay, so then it's connected. It's called planar. Look at the spelling. If there are none of those edges that are crossing. When a planar graph is drawn in this way, it divides the plane into regions, which is called faces in graph theory. So I just want to remind us, here we had two graphs. You can remember this. This graph has no edges that are crossing it. But these two graphs are isomorphisms. They are the same graph, just drawn differently. They share the same structure. Okay, the same one with the one at the bottom. This is a plane graph, P-L-A-N-E. This is a planar graph, P-L-A-N-A-R graph. Why do we say that? Well, we can unscramble this, or we can draw it differently. There we go. So that there's no sides crossing. The same with this one. We can take that up and we can do that. There we go. Same graph. Then there's no sides that are crossing. So we've changed a graph that was like this, which was a planar graph, into a plane graph, P-L-A-N-E graph, by doing what we just did. Okay, so let's just close that and let's go on to our focus. It says here, when it is possible to draw a graph so that none of its edges are crossing, when is this possible? Okay, well, if this is possible, we call it planar. Notice that the definition of planar includes the phrase, it is possible to. Okay, important stuff. This means that even if a graph does not look like it is planar, it still might be planar if you can do what we did here. We redrew a version of that over here so that the sides do not cross one another. Okay, when a planar graph is drawn without edges crossing, the edges and vertices of the graph divide the plane into regions. Now, in our book, we're going to talk about these things as the regions as an F. Okay, we call these each region a face of the graph. Now, that becomes quite relevant when we're going to look at polyhedra, where we talk about the faces of the polyhedron. Okay, the number of faces does not change no matter how you draw the graph, as long as you have the edges, like he said, that does not cross with one another. Okay, so it makes sense to ascribe a number of faces as a property of the planar graph. Okay, the number of regions is a property of a planar graph. Now remember, just to remind yourself, the regions are how the graph divides the plane. Okay, so he says here, we can only count faces when the graph is drawn in a planar way. So in other words, when it is a plane graph, then you can count regions. Okay, so here he gives us an example. We have a graph with 4 vertices and 6 edges. There are 2 vertices that are crossing, so it's not in planar plane. It's not a plane graph, P-L-A-N-E, but it could be planar. So in other words, how do we find out if it is? Well, we try and redraw this so that there are no edges that are crossing. I'm looking for my pencil here and I must have misplaced it or put it somewhere else. So I'm going to use a green pen here. This is possibly planar. It's definitely not a plane graph because there's this edge crossing happening. How do we know what to do? Well, there's a valence of 3. Here's a valence of 3. There's a valence of 3. There's a valence of 3 over there. So what should I have? I should have 4 vertices, each with a degree or a valence of 3. Once I've redrawn this. So all that he did was remove this side, and instead of taking it across, we take it around the figure. Then this is a plane graph. A plane graph is planar. Okay, so it is both of these. Now look at your vertices. Valence 3, valence 3, valence 3, and a valence of 3. Okay, so if you try to count faces using this graph, you'll say there's 1, 2, 3, 4, possibly 5 faces or 5 regions. I'm going to talk about a face as a region. Okay, so you could possibly say that there's 5. But if you look at this graph, there's 1, 2, 3 regions instead of 5. Okay, and that is what those vertices do to the graph, to the plane actually. We've got 1, 2, 3, and the 4th plane is what lies on the outside. So let's just quickly write that down here for you. We had the one running across, we had 4 vertices, and instead of running this one across, we could have run it that way. Okay, so what does this do? It divides the plane into region number 1, region number 2, region number 3, and on the outside is where we locate region number 4. Okay, folks, so please make sure, let me just remove this here. Please make sure that you understand the language. These regions are going to be represented by F's in our work going forward. So let's have a look. So there is a connection between the number of vertices. There we go, the number of vertices V. So there's a connection between the number of vertices, which we will call V, and the number of edges, which we will call E. So the number of edges, which we will refer to as E, and then the number of faces or regions that the plane has been divided into by that plane graph, and that we're going to refer to as F. Well, that relationship, folks, is resulting into something that we're going to look at just now. It's called Euler's Formula. Now, Leonhard Euler, who is the father of graph theory, folks, he didn't just focus on graph theory. There's a lot in your mathematical lifetime. You're going to come across a lot of things that are named after Leonhard Euler. He was a very gifted and talented mathematician. Okay, so let's continue with our discussion here. Let's just stick to planar graphs for a few minutes longer. If I have a graph that looks like this, okay, that's a planar graph. It's not the simplest of the planar graphs. The simplest is a vertex. Then we have 2 vertices. Now, what this vertex does, it has one vertex, so the number of vertices is 1, and it just divides the plane. Now remember, these 2 are not there. Divides the plane into one region. It's just the region around the dot. Okay, so there will be one face and one vertex. If we look at that, we've got 2 vertices. Okay, those 2 vertices, if I join them with an edge, does not include or does not form a circuit. Okay, so all it does is it has 2 vertices. V is 2, it has one edge, V is 1, and one region still. It's so only the region that runs around it. It's only when we bring in our third vertex that we have a diagram that has divided the plane into region 1, and on the outside of that we'll find region 2. Okay, so here we'll have 3 vertices, we'll have 3 edges, and we'll have 2 faces. Here we'll have 1 vertex for the dot only, and we will have 1 face, the area around the vertex. Here we'll have 2 vertices, we'll have 1 edge, and we'll have 1 region or face that this particular graph divides the plane into. Now, something interesting that we can remind ourselves of is if we have a tree. Now, remember what a tree is? A tree is a connected graph with no cycles. So if I do that, and let's just gooi another vertex there and come this way, that is a tree, okay, because it has no circuits and it has all its vertices of the original, so we can also refer to this as a spanning tree. Okay, so what does that do? Well, there's 1, 2, 3, 4, 5, 6, 7. 7 vertices. There's 1, 2, 3, 4, 5, 6. Remember, the maximum number of edges that a tree can have is 1 less than the number of vertices that that tree has. That's why it's called a tree. But there's still just 1 region that this tree has, and that's the region. There's no cycles, hence a tree. So it just has the area around it as the region that it's divided into. So we can say that every tree can be drawn as a plane graph with 1 region, an unbounded graph. That's a bounded graph. Why is it bounded? Because it bounds a region with 3 edges, and it could have had 4. This is a bounded graph as well. Okay, by the way, we can draw triangles for each one of those regions. The region is defined by 3 vertices. A triangle is defined by 3 vertices. Just bear that in mind. Okay, so what is a boundary then, or bounded graph? A boundary or bounded graph is a region in a plane that has a set of vertices and edges that include that region. Okay, there we call those 3 edges the boundary. Now, we've done quite a few of these already to see how this works. So I'm just going to pause because I actually dropped my pencil. Okay, I'm back, pen in hand, and we can continue our discussion. Okay, just one thing I need to also mention. Earlier we had a graph that we worked with. I'm just going to draw any graph here. This is a graph with a vertex on the inside, so we have that situation. We've got vertex 1, 2, 3, 4. So in this case, there's 4 vertices. There's 1, 2, 3, 4, 5 edges. And there's region 1, region 2, and then on the outside there's region 3. So there's 3 faces to this graph. Okay, so this is a plane graph, because there's no edges that are crossing. Okay, now folks, we can draw this graph differently. We can take that vertex and put it on the outside. So we'll have something that looks like this. So the 2 graphs again will be isomorphic. Okay, there we have the 4 vertices joining each other. Now remember, if I move that out, there's that line that lies across. Now let's see how that changed our situation, if at all. We still have region 1, region 2, region 3. So yes, there's 3 faces to this, or 3 regions. There's still 1, 2, 3, 4 vertices, and there's 1, 2, 3, 4, 5 edges. So what do we have here? We have different plane graphs. These are what we call different plane graphs. And clearly, because the graphs look different. They don't look the same, but they both are plane graphs. Okay, so that's the first thing to notice. The second thing to notice is that they are isomorphic. Okay, so why do we say the graphs are different, folks? Their boundaries are different. Okay, that moves to the outside. So these two boundaries here formed part of this region. So region 2 had 1, 2, 3, 4 boundaries. Region 2 now has 3 boundaries. So there are plane graphs, both of them. They are isomorphic plane graphs, but they're different graphs in the sense that they don't look the same, or their boundaries are different. Okay, so now if we go to a graph that we've worked with before, and that is the graph where we had the houses and the utilities. So we had the 3 houses at the top, the utilities, and if I call this house 1, house 2, house 3, utility 1, utility 2, utility 3. I think if you can remember this graph, you will also remember that it is definitely not a planar graph, or it's not a plane graph. We want to find out if there's a possibility for us to draw this graph so that there are no edges, or no lines crossing. I'm missing a line here. That's the line from house 3 to that utility. So you can see there's quite a few crossings there. Okay, so we want to know, this is a bipartite graph, by the way. Remember what bipartite refers to? That you can separate your sets of vertices into 2 very distinct sets that are not connected to one another. Okay, so this is a complete bipartite graph. We have seen earlier that this graph isn't planar. Now let's just see why. Okay, if I use I redraw this graph, I can draw it in, you can see it goes alternate, alternate house, then utility, then it can go house, utility, house, utility. So I can have house 1 here, I can have utility 1 there, then utility 1 goes to house 2, and house 2 goes to utility 2, then utility 2 will go to, so what I'm doing is I'm drawing a graph that appears to be planar, okay, or plane graph. So here's house 3, and there is utility 3. So in this graph, none of the bipartite sets are connected to each other, so they are still adjacent. So remember, what is a way to draw a bipartite graph? Is to look at an edge and put the one vertex in the one edge set, the other vertex in the other edge set. Okay, so I can now also, I don't want to join house 1 with house 3 because that will make them adjacent. So I'm just going to join house 2 with utility 3. So far we're fine. We've got 1, 2, 3, 4, 5, 6 vertices. Okay, we're trying to see, is this a planar graph? In other words, can we draw the graph so that there's no crossings? House 1, I want to now connect with utility 2. So I can do it this way, and still there's no lines crossing. And this is where we hit a snag here. Because if I want to join house 3, I can only, it's already joined to utility 2 and 2 and 3. I would like to join it to utility 1. If I go across like that, I'm crossing over here. If I go around like this, let's go the other way around here, I will need to cross into that path to get to utility 1. So either way, I have lines that are crossing. Now folks, this you can look at it with the pigeonhole principle if you want to, but it doesn't matter what you're going to do. Okay, there are more lines necessary to join these every house with every utility. Okay, so what we have here is a graph that definitely is not planar. No matter how you look at it, the graph will not look planar. So let's look at why it was important, our discussion of what we have at the top. Okay, we've established that there is a connection between the number of vertices in the graph, the number of edges, and the number of faces. Okay, that connection is called Euler's formula, Eulers formula. Euler, I don't know what the pronunciation is. Some people say Euler, other people say Euler. Okay, so we'll just go with what sounds nice. I like Euler. Okay, so what does Euler say about the planar graph? For every connected planar graph, now all the graphs that we were looking at here are connected graphs. Okay, this is not the same graph. That's one graph, two graph, three graph, four graph, 5, 6, 7 graphs that we've got down there. So it has V vertices, E edges, and F faces. Euler said they behave in the following way. The number of vertices minus the number of edges plus the number of faces will always give you a total of 2. That is what Euler's formula say. Now we're going to prove that just now. Let's just see with the graphs that we've got up here, is that indeed the case. Okay, so the first graph had 1, 2, 3, 4 vertices. It had 1, 2, 3, 4, 5, 6 edges, and it had 1, 2, 3, 4 regions. Okay, and the regions are F. So if I put that for graph 1, if I put that in there, I get 6, what am I saying? 4 minus 6 plus another 4. Now that gives me 8 minus 6. So indeed, that is true for the first graph. Okay, the second graph, the triangle over here. If I look at that, it has 2 regions. So the F is 2. It has 3 edges. So I'm going to subtract 3. Sure. Those are my number of edges. And then I have 3 vertices. So 3 minus 3 is 0 plus 2 does indeed give us the 2 for graph number 2. Well, let's look at graph number 3, which is this one over here. Graph 3 had 1 vertex, no edges. So 1 vertex minus no edges plus 1 region again gives us the 2. Now folks, I think Euler must have been very, very creative and know what to look for to try and find generalities like this. Let's look at the third one. There's 2 edges, so let's start with the vertices. There's 2 vertices. Number of edges is 1. The number of regions, 1. And that again gets us to 2. Okay, so far, I don't think let's do one more. Let's do this one over here. Let me get another color here from my collection of colors. I'm going to go for red. Okay, 1, 2, 3, 4, 5, 6, 7 vertices. So 7 minus the number of edges, which in this case, this is an E and not a V. So minus 6 plus 1 region gives us a total of 2 again. So we have it being true for graph number 5. Okay, so I think at this stage it will make good sense to try and prove what Euler's rule is saying. Okay, so let's attempt a proof. Okay, so we're going to say let G be a connected plane graph. Okay, so meaning it has no edges that cross each other, with V vertices and E edges, and finally F regions or faces. Okay, what do we want to prove? We are required to prove the relationship that the number of vertices minus the number of edges plus the number of faces will always be a value of 2. Okay, now our proof will follow. Okay, we're going to prove this by induction. We're going to use induction, and we're going to use induction on the number of edges that the graph has. Okay, so we will use induction, and we will use induction on the number of edges that we have. Okay, so let's look at our base case. Our base case, if E is 0. Now folks, that just means there are no edges. So it is similar to the graph we had over there, where there's just a dot. Okay? Then if the edges, the number of edges is 0, we have one vertex and one region that remains. So V is 1 and F is 1. So that one vertex divides it. So then, if I look at the relationship V minus E plus F, it will be 1 minus 0 plus 1, which is indeed 2. Okay? Now remember, this is a connected plane graph with no edges, the case where E is 0. Okay? So what graph did I look at? The graph is the K1 graph, connected graph with one vertex. Okay, so now follows our inductive hypothesis. Suppose the theorem is true. Okay, so we're going to suppose the theorem is true for all connected plane graphs with fewer than E edges. Okay, with fewer, and that's fewer than E edges, but still maintaining that E is now bigger or equal to 1 because we've dealt with a base case. Okay, so now we consider a plane graph G with E edges, V vertices, and F regions. Okay, just pretty much just setting up the whole argument. Now here we've got to go and we've got to work with two cases. In the first case, now remember, we had graphs here that were cycles, that contained cycles, and we had graphs that contained no cycles. So we're going to distinguish between those two graphs. So our first case, case number 1, the easier one of the two. If G is a tree, Now remember, if the graph G is a tree, there are no cycles. So there's only one region, irrespective of the number of edges or vertices. Okay, so if G is a tree, then E will be the number of edges, will be the number of vertices minus 1. And there's one region that we have that the tree divides the plane into. Because it's a tree, the number of edges is always one less than the number of vertices, and F means there's one region that this whole thing is dividing the plane into. Okay, so what can we say? We can say that what is V minus E plus F? In this case, it will be V minus E, and E is V minus 1, plus the 1 region. So this is the easy of the two cases. So V minus V is 0, minus 1 times a minus is a plus, 1 plus another 1 is 2. Okay, so this holds true for any tree graph G. Okay, so now case number 2. Slightly a little bit more complicated than case number 1. So what happens if G is not a tree? Okay, this is the first case. If G is a tree, G here is definitely not a tree. Okay, so what does the theorem say? The theorem says we must have a connected plane graph. Okay, so what do we know? We know G is connected and must have a cycle because it's not a tree. Okay, it must have a cycle, at least one cycle, we can say. Okay, and we will call that cycle C. My pen is slipping. Okay, so now we will remove an edge. We remove one edge from this cycle, okay, and apply our inductive hypothesis to the smaller group without having created a disconnected graph. Okay, so the edge that we're removing must not create, and the edges are E's, now remember. So we remove an edge from C so as not to create a disconnected graph. That's very important, because if you create a disconnected graph, you are not doing the right thing. So you're removing a bridge. Okay, remember what a bridge is. We spoke about that earlier. A bridge is that one edge that you can remove to take a connected graph and form a disconnected graph from it. Okay, so this edge E is not a bridge, very important. Okay, so the graph minus the edge E, so we'll write it as that. The graph minus the edge E is still connected. Okay, because we didn't remove a bridge. And it is still planar, because it was a plane graph to start off with. Okay, did we remove a vertex? No. So with V vertices and E minus 1 edges. Okay, and because we've removed an edge, now let's just look at what happens if I remove an edge. If I take that edge away, folks, then I'm collapsing two regions. If I take this edge away, I'm collapsing those two regions. If I take this edge away, I'm collapsing these two regions. So what happens if we remove an edge? Once we remove an edge, we have F minus 1 regions. left in our new graph. Okay, so now let's just see, what does this mean for Euler's rule? So what happens? V minus E plus F will be, this number of vertices are the same, minus the new number of edges plus the new number of regions. What happens there? We'll have V minus E plus 1 plus F minus 1. So this is still V minus E plus F. And what is that? That is equal to A2. Sorry, I went off the screen there. So fact is, folks, this holds true for any connected planar graph G that is not a tree. And that settles it. By the principle of mathematical induction, it will therefore hold true for what? For any connected plane graph with V vertices, E edges, and F regions. This rule will always hold true. This is the rule that we proved. How did we prove it? We proved it by induction. We did our base case where there's no edges, and then we went and looked at the inductive hypotheses where there's one edge or more. That divided into two cases. Case number 1 where G is a tree, and case number 2 where G was not a tree. Okay, and by our inductive hypothesis, we have shown that that is indeed always going to be the case. Okay, let me see, what are we going to look at next? Next we're going to start focusing on non-planar graphs. So please remember to like the video and also to subscribe to my channel.